Hi everyone, my name is Gustavo from Brazilian Doping Control Laboratory. Today I am talking about the project funded by PCC that is in progress, and I'm working on it with Professor John Macklin and his research group from Vanderbilt University. Basically, this project deals with ion mobility spectrometry in steroid analysis. In this slide, I'm showing anti-doping figures of merit reported in 2019 by WADA. The first table on the left side are the substances identified as AAF in substance group. As you can see, the athletes have a preference for anabolic agents when they are looking for boosting their performance in sports due to their anabolic effect. The major steroids are widely metabolized in phase 1 and phase 2 metabolites. Then the misuse of steroids is tracked through their metabolites in doping analysis. Recently, phase 2 sulfated metabolites of steroids have been demonstrated the potential to enlarge the detection window of steroids in doping analysis. In this slide, for example, Gomes and colleagues described a new long-term metabolite of methanthionine excreted as sulfated metabolite. Unfortunately, the enzymes usually employed in doping analysis don't have reasonable sulfatase activity for removing it. Alternatively, chemical hydrolysis in acidic environment is carried out. Nevertheless, the yield of this reaction is low. Because of this limitation, LC-HRMS has been employed to directly detect the intact form of sulfate metabolites and glucuronide metabolites also, which are hydrolysis resistant, for example. But usually the tandem mass spectra of phase 2 metabolites provide few fragments ions only. Then the reliability during the identification process for these metabolites might be compromised. Due to these limitations presented in the previous slides, ion mobility can be used as a straightforward analytical tool to reinforce the metabolite annotation. Ion mobility spectrometry is a gas phase separation technique that distinguishes ions according to their size, shape, and charge state. Ion mobility spectrometry separations occur post-ionization in a defined mobility separation region filled with buffer gas. So these ions traverse this region under the influence of an applied uniform electric field, varying their migration time through the gas, called drift time, is straightly correlated with ion size, and the measured size is commonly described as the ion's collision cross-section, CCS. Ion mobility offers extra dimension for compound separation, providing a higher peak capacity when it is associated with LC-HRMS. This extra dimension can reduce the noise level and increase the separation efficiency of the analytical method. Ion mobility combined with LC-HRMS can exclude stereoisomers interference, which is not fully resolved by LC-HRMS techniques alone. And CCS is an intrinsic molecular descriptor of gas phase surface area. Then it can be used also as an identification point for steroid target analysis. Thus, this parameter can increase the reliability of some identification process usually faced in doping analysis. In this slide, I'm showing some preliminary results. The figure on the right side, specifically panel B, is showing the peak capacity of ion mobility. In this case, was observed isomer interference at the retention time of long-term metabolite of methyl testosterone. As you can see in the figure, this interference is not well resolved by high-resolution mass spectrometry alone, panel C. However, when the data were extracted employing the drift time dimension, the separation was achieved. The accuracy obtained in the spiked urine sample was less than 1% when compared to the pure reference material. This value is within the margin of error for drift ion mobility analysis. The high accuracy reached in this case showed also that urine matrix didn't affect the CCS measurement. Thus, excretion urine samples could be used as a surrogate for CCS measurement when reference materials are not available. The usefulness of ion mobility was also demonstrated for analysis of two long-term metabolites, the glucuronide metabolite of drosonolone and stanozolol. The combination of LC, ion mobility, and mass spectrometry removed the interferences which can jeopardize the isotope distribution patterns of these metabolites. This feature can be used also for compound annotation. Thus, these data show the ability of ion mobility dimension to provide additional selectivity and confidence in analyte identification. As conclusion, these results that they use CCS as a molecular descriptor in addition to accurate mass and retention time has great potential for identifying the intact steroid phase 2 metabolites. The preliminary results show the possibility to use excretion urine samples as a surrogate to determine CCS with reasonable accuracy for those cases when reference material is not commercially available. We are evaluating at this moment the supposed benefit of ion mobility in the sensitivity parameter. For target analysis and analytical workflow, applying machine learning approach for CCS prediction will be quite helpful in the future. Thank you for your attention.